Welcome to the Albatross test briefing. Beginning with the weight and balance test, you can see that the CG experimental position lags slightly behind the actual CG location. In terms of limits, at a location of 0.16 and minus 0.34, the Albatross will tip over. Now looking at thrust calibration. As you can see, as RPM increases, so does thrust, up until a maximum value of 27 newtons at 100 RPM. At 5 RPM, the value of thrust drops to 0. These are the control inputs used to configure the Albatross and its flight instruments correctly. These control inputs can be validated by looking at an elevator input check. A negative elevator deflection gives a positive angle of attack, and conversely, a positive elevator deflection gives a negative angle of attack. Each cycle represents a maximum positive deflection of elevator input and a maximum negative deflection of elevator input, and the corresponding angle of attack is then shown in blue. Each cycle represents one wind speed, with wind speed increasing from 10 meters to 20 to 30 to 40 to 50 meters a second across the 5 cycles shown. As can be seen, the angle of attack as a result of elevator input angle is largely invariable to wind speed. This time, each cycle of maximum input elevator angle for positive and negative deflections represents a different CG location, with CG location moving further forward as the chart progresses from left to right. As can be seen, as the CG moves further forward, the amount of oscillations of angle of attack decrease, and a short frequency period of less than 1 second can be observed, which ties up with the Albatross handbook data. It seems to be stable for all central gravity locations, and therefore they should all be fine to operate with. This chart shows how roll rate varies with incoming wind speed. As the incoming wind speed increases, the roll rate increases, and as a result of this, the frequency of the angle of attack oscillations also increase. This chart shows how the heading angle varies with rudder input. As the rudder is deflected to the left, this causes motion of the aircraft to move to the right, and as the rudder is deflected to the right, this causes the aircraft to deflect to the left. The pitch seems to be more heavily damped than the yaw, with the heading angles oscillating after a maximum input of rudder. This chart shows what happens when the engine is switched from 0 RPM to 100 RPM and back down to 0 RPM for different CG locations with respect to the thrust line. As the CG location is moved from high to low, the amplitude of the angle of attack variation remains largely the same. However, the trim angle of attack condition seems to increase as the CG is moved to a lower location. This chart demonstrates how lift coefficient varies with angle of attack for different flap deflection angles. As the angle of attack increases, the lift curve slope increases up until an angle of 13 degrees, at which point the peak lift coefficient can be found. The lift coefficient is largest for a flap deflection of 40 degrees and is smallest for a flap deflection of minus 40 degrees. The maximum lift coefficient achieved is 1.2, which ties into a similar number which can be found in the Albatross handbook. This chart shows the lift against drag through a clean configuration. This means no flap deflections and the standard 20 meters per second wind speed. These two charts show how lift to drag ratio varies against lift coefficient for different flap deflection angles. Lift to drag ratio is greatest for positive flap deflection angles, and the greatest CL can be found, or the greatest lift to drag ratio can be found at a CL of 0.6. The more negative the flap deflection angle, the smaller the CL achieved. The largest lift to drag ratio is vastly different to the manufacturer's handbook, where the largest lift to drag ratio in this case is 15, whereas in the handbook it is suggested that the largest lift-to-drag ratio achieved is 30. This chart shows how coefficient of moment about the centre of gravity varies for different elevator deflections against the lift coefficient. For a coefficient of moment of 0 about the centre of gravity, the full range of -40 to +40 degrees of elevator deflection angle can be used to trim the aircraft across all ranges CG which the Albatross will endure. Okay, so this is the Albatross manoeuvring on the ground. It is found that as soon as the Albatross is able to move, that rudder deflections can be used to control the direction of the Albatross. The Albatross is now taking off, and as it's building up speed and pulling back on the flaps, lift-off speed of 20 meters per second can be used to lift off the Albatross. It is now going to its maximum speed where it reached 39 meters a second. This portion of the Albatross shows how the Albatross was trimmed and used to perform a bank turn. The Albatross is now making its way through the flight test course using the inputs used in the previously defined slides to move through the slalom. The steady speed of between 26 meters a second and 28 meters a second has been aimed for throughout this course, as lower speeds have been found to make the Albatross more difficult to fly. The speed of the Albatross is now reduced to find out the slowest speed at which it can still fly. At an engine off configuration, the Albatross begins to lose speed, and this eventually drops to 26 where the glide ratio forces it to hit the ground.